And I will stay with magnetics in films which are geometrically curved in my talk, but I will primarily address the topic of sensors, so like application aspects of those thin films. As you can see, we benefit from a broad network of collaborations, and what is quite remarkable here that I just realized from the talk of Denis Sheka, that the team, the rhythm team, is very well represented also here. Just have a look, and also list it's of course Denis Sheka, Vladimir Kravchuk, Alexander Pilipovsky, Alexei Volkov. So basically many people who are members of a rhythm team are still very well involved in all this research. And I'm very, very thankful, of course, for Yuri and Denis for putting up this team together and, of course, promoting young researchers. So what I will primarily discuss in my talk is several different interactions which stemmed out of this interaction. For example, it's not only curvature effects, it's not only vortices or skyrmions, but now what we are discussing with a group of Denis Sheka is also a lot of activities on antiferromagnets, also magnetoelectric antiferromagnets, magnetic domain walls. So basically different types of excitations in also differently ordered, also flat materials. And this is beautiful to have this network which emerged over the last, I don't know, about 10 years, which we worked together starting from 2013 with Yuri and his team very, very intensively. So the talk is primarily focused on curvature effects. This is, of course, a lot of fundamental activities which we are doing together with a group of Denis and Vladimir. And I will not cover this topic in my talk. I will simply put this slide, which I find very like representative of this very intense collaborations where theory and experiment goes hand in hand together, from very beautiful predictions, theoretical predictions. Just have a look, Alexander Pilipovsky, Vladimir Kravchuk, Denis Sheka, to theory and experiment, where this experiment or theoretical predictions are confirmed to the beautiful work of Alexei Volkov on the parabolas. So this is not only theoretical abstraction as one can think of it. It's really beautiful physics which one can observe in experiments. And this, I think, what makes this work as a research direction, as Vladimir mentioned in his talk. So on our side, we are trying to support these activities on experiments. It's a lot of things to explore, starting from the fabrication of these objects, which can be prepared in many different ways. It can be tubular shaped objects, it can be helices, it can be hollow tubes or cylinders, it can be hemispherical caps. When you fabricate them, of course, you have to pose like your question, how to characterize them, because they are three-dimensional, they're mesoscale objects. So how you can now characterize, for example, evolution of the main pattern on such kind of even simple tubular objects. You need to see the mains at the front side or the back side at the sides of this tube, and how do they evolve. So these tomography approaches, they come very, very naturally into discussion at the moment. So it's not only theory, it's a lot of really fundamental discussions and discoveries in methods, how to fabricate and characterize these films. And of course, if you can fabricate them, then you have to put this question, as we heard to the talk of Vladimir from our chair, where can you use them, right? So this beautiful physics, obviously beautiful physics, very strong. Where can you use them? There are plenty of different ways where you can apply these films. Something which I will address in my talk is sensor activities. So basically, if you have a geometrically curved magnetic thin film, obviously you can make it curved, put it on skin or integrate in textile. And in this case, you address questions of the community which is working on the field of flexible electronics. We work on healthcare, so we basically implant such kind of flexible devices, consumer electronics. But here I will primarily focus on magnetic field sensors, which are geometrically curved. So let's talk about skin conformal magnetoelectronics, how to fabricate, what are the application examples, and at the end I will tell you why do I actually explain this during the talk about the memory of theoretical physicist. Yeah, so a couple of words: applications of magnetic field sensors, magnetic materials, very broad, right? Permanent magnets, electronic compasses in smartphones, hard disk drives, basically switches in fridges or coffee machines. So this is all of these magnetic field sensors. So basically, there are plenty of ways how to fabricate magnetic field sensors: Hall effect, magnetoresistance effect. If you think about hard disk drive, that would be something related to giant magnetoresistance effect, spin valve sensors, TMR, memory cell like elements. And the idea here is to deposit magnetic multilayers with a thickness of, let's say, in a nanometer scale on different substrates. Typically for standard reports, you deposit them on wafers, like silicon wafer or glass substrates. What we deposit them on flexible foils, because if you want to have a flexibility, the substrate should allow for flexibility. And in this case, taking polymeric foils of different thickness, let's say 1 to 100 micrometers, you can still use it as a substrate to perform thin film deposition, lithography, to define the sensor structure, to define contact layouts, how to integrate, interface these sensor elements to the outside electronics to be able to communicate with these flexible sensors. In principle, it looks like this. Just imagine you have a very thin foil, like a couple of micrometer thick polyethylene, and you prepare your integrated sensor on this foil, right? It's transparent, it's very nice, it's very flexible. You can put it, because of flexibility, on any kind of surface which is curved, including skin or textiles, for example. And then what is important in this type of research is that you have to do magnetotransport characterization as usual, because it's a thin film, which is magnetic thin film. You have to understand what is the change of resistance in a magnetic field, which you call magnetoresistance, but at the same time it's flexible, so it's mechanically flexible object. And you have to understand, of course, how stable is this mechanically flexible sensor or thin film upon deformations. And the standard characterization, which is always happening in the background of this spintronic or curvilinear spintronic community, is that you have to bend your device and characterize the change of resistance, not only in the field, but also upon mechanical deformations or magnetoresistance, and also how robust it is. Because just imagine you just put it on your skin, then you start moving your hand, and of course, upon such kind of repetitive deformation, the sensor still has to remain a magnetic field sensor, but not a strain sensor, because of magnetostriction effects, for example. And of course, the idea is to fabricate sensors which are magnetic field sensors, but not the strain sensors. About thin films and all this geometrically curved thin films, you can fabricate them very, very high quality. What does it mean? So in principle, in transport, it means magnetotransport means that the sensor remain not noisy upon operation. So if you will take example, very simple example, planar Hall effect sensor, it's a basically derivative of anisotropic magnetoresistance effect. 20 nanometer permalloy, nothing special. You just put it on flexible foil and now you start bending this in, right? So it's an absolutely standard racetrack, what you do, but you just put it on flexible thin film. And if you will measure performance of this device, you will see that even on polymeric foil, you can get very good stability of the sensor device. It can resolve something like several tens of, let's say, sub-100 nanotesla magnetic fields. Now, if you will have these numbers, it's very interesting to compare what does it mean. So just think about, just have a look on this plot on the left. In order to enable sensitivity of magnetic field sensor upon mechanical deformation to be able to resolve sub-100 nanotesla magnetic field, it means that longitudinal resistance, basically standard resistance which you measure, has to be very, very stable. So no striction effect, no cracks has to appear there, right? And if you will pay attention to these red symbols at the left-hand side diagram, you will see that the change of electrical longitudinal resistance is less than 0.1 ohm for the background of 118 ohms upon mechanical deformation. It means that if you will properly design your spintronic elements on flexible substrates, they will be mechanically stable with an accuracy better than 0.1%. And this is a stability which you need in order to be able to resolve in a transversal channel, basically in a Hall channel, the effect of magnetic field, which is sub-100 nanotesla. And this mechanical stability can be enabled, so this is experimental result here, if you will realize your sensors on ultrathin foils. And the beauty here is that the strain can be minimized in a metal thin film if you fabricate it on substrate which is very, very thin. So reducing the substrate, in this case, it's not something which is very exotic, it's physically motivated case. Yeah? So if you want to have your curvilinear spintronics, you need to reduce the thickness of the substrate. If you have such kind of sensors, which are geometrically, mechanically flexible and also very, very sensitive, you can just put them on any kind of surface. This is a specific example when you put it on skin. What is important, it remains very robust. So it's a magnetic field sensor, which is a GMR in this specific case. You can jam it, you can bend it, you can do whatever you want to it. Without encapsulation, it's stable on the foil, and it performs as a magnetic field sensor as on silicon, rigid silicon wafer. Now you have to ask a question, where can you use it? There are plenty of different ways where people explore this, and even commercially. But something from the fundamental point of view, what I find very, very exciting is to try to use this curvilinear spintronics for enabling artificial magnetoception for humans, right? And there are plenty of ways why, or reasons why you would like to do this. One of them is super trivial, because in this case, you can start navigating as birds, for example, or different animals using geomagnetic fields. This is a trivial explanation, but still a valid one. Something which is maybe more appealing is realization of human-machine interfaces, where you can explore the interaction of this wearable devices with external magnetic fields in order to realize, let's say, interfaces, how you can operate with virtual objects. And this is very important for all the social reality networks, meta universe, what Facebook is now becoming, right? And of course, it's important for prosthetics. Of course, it's important for rehabilitation and medicine. And a couple of things I will just sketch now in my talk. Idea here is very simple, because magnetism does not require touch-based or tactile interactivity. It's a field interaction. It means that you can interact with a piece of permanent magnet without touching it. This proximity sensing, but also angle sensing, what you use in electronic compasses or just standard compasses, that's exactly the minimalistic interactivity which you require in order to interact with surrounding, right? And this is simply granted by magnetism. Therefore, it's very natural to realize human-machine interfaces based on motion sensors provided by magnetic field sensors. And this is only a couple of examples. How does it in principle works in the lab, right? So just imagine that you have a piece of permanent magnet. The scene in black is just a fridge magnet, a couple of millitesla strengths of the field. And in this case, as you can see, without touching this magnet, you can transduce the information on a distance to the source of magnetic field to electronics. And now it's up to you how you want to use this information, right? You can use it as a proximity sensor, as a simple button. Just imagine how you interact with your smartphones. You're pressing there. That's a simple button. You can, of course, put it not only on the skin of humans. You can just decorate it the prosthetic devices. It's important for robotics, right? Because robots also should interact with humans. They also need to have this proximity angle sensing, which can be enabled by magnetic fields. Of course, if you think about full-fledged interactivity, proximity sensing by itself is not sufficient. You need to have angle sensors. Again, spintronics allows you to do this. Question is, can you do it on flexible foils? And the answer, as you can see here, yes, you can. You can do. Is there something important in chat? Do I need to answer? Or...
Excuse me, please, if I may interfere.
Yeah, sure.
And also Jens, dear participants, could you please mute your mics if you are not speaking, if you don't intend to be heard, because we have some phone. Thank you very much.
Oh, okay. Thank you, Larissa. Thank you. Yeah. So if you think about full-fledged interactivity, of course, spintronics can help you with this. And in this case, you can really realize more or less credible interaction interfaces where using geomagnetic field or interaction in geomagnetic field using such kind of curved magnetic thin films can allow you to interact with these virtual characters, right? It's very, very simple. You don't need to touch anything. You don't need goggles for virtual reality or motion restraining gloves. curved thin films which are mechanically stable, it's something which can do already the trick. What is important about magnetism, and sometimes it's simply overlooked, that magnetism has counterparts of standard electronics, like transistors, right? And if sensor is a very special device because it senses linearly the field, there are also spin valves, as for example, magnetic switches, right? It's a simple basic element of any kind of logic circuit, like transistor in electronics would be spin valve in magnetism. And it means that you can simplify design of circuit using such curved magnetic spin valves, sensors, which can take a lot of logic, so basically decision-making process in a simple metal stack, which is curved on the foil. So what you see here is a standard stack of synthetic antiferromagnet, which is basically put together with an out-of-plane spin valve. So you have a copper spacer layer separating pinned reference layer and the free magnetic sensing layer. And now what you do, you play a trick simply by playing with the thickness of the copper layer, because in this case, you can modify the coupling between pinned and the free layer, and the spintronic properties of the spin valve becomes very, very much affected. So if you will have pay attention to this green curve in a panel F, you will see that it's a simple switch, right? So you just saturate it in a high enough magnetic field, it will retain its high magnetoresistive state. If you will saturate in a negative field, it will be a low resistance state. And using this very simple knowledge, which is basically a textbook example, you can already realize such kind of virtual interfaces, which can really disregard all environmental disturbances, because there's a lot of magnetic fields around. If you will be curious, just please measure magnetic field from your smartphone. If you have even last iPhone, it's 20-30 millitesla disturbances in the vicinity of magnetic, basically of the smartphone. Huge disturbances in an environment. Very difficult to make a reliable electronics working on, especially this flexible, which works reliably in such kind of real settings. And with spin valves, which can simply disregard the non-useful information, you can easily do such kind of demonstration where you can realize, I don't know, magnetic button, which can switch on the display, actuate display, and then you can simply hover over this array with the sensor without disturbing the sensor input. You can switch off when you don't need it. The same trick you can apply if you will simply reduce, this example I like even more, because you can just reduce the thickness of the copper layer, you enhance coupling, and then because of near roughness, you will have also the shift of hysteresis loop, this red curve here in panel F. As you can see, it's simply shifted from zero field. That means, like for like a interpretation of this curve, is that this spin valve will respond only to magnetic field of specific polarity, right? So that's what it will do. And this allows you to, again, realize something which is very useful for standard scenarios. Just imagine you are jogging, right? You are somewhere in the forest, you want to see the map where you are. And of course, you don't have too much battery life and everything. You want to reduce the energy consumption of the screen. So what you see, you just approach the magnetic button in this case, and the screen will be on only during the time when the finger is basically next to the button. As soon as you remove finger from this button, the screen will disappear. So you will stop draining the battery, right? So such kind of interfaces you can realize with a very simple spintronic elements like, for example, spin valves. If you think about smart skins, usually you think about human skin. And this is, to be honest, the smallest portion of activities which is happening worldwide in smart skins. Primarily, it's a robotic skins, actually, for different machines, different interfaces, human-machine interfaces, but primarily on the robot side. There is only a very interesting side of robots. It's not only this heavy, bulky metal pieces which are around, right? There is something which is very exciting going over, I don't know, last 10 years or 15 years, where people start to develop soft actuators. So this is nothing more than, let's say, rubber piece which you can somehow functionalize in order to make it actuatable. Chemically, thermally, pneumatically, it can be actuated. Also magnetically can be actuated. For magnetic actuation, you need a composite, which is nothing more than the rubber, for example, with embedded particles, which are magnetic. And in this case, you can use external magnetic fields to drive these robots. You can just magnetic fields or magnetic field gradients to drive these robots. If you will play with the thickness of these robots, you can realize something which is very, very unique. Unique in the sense of how these devices can interact with very, very fragile objects. So here you can see an insect. Just imagine other biological species, which are even maybe on a micro scale. And these robots can interact with this species, but they cannot destroy them, right? So they are soft enough, for example, to interact with them very gently. And this is important for exactly the operation with cells, for example, living cells. They don't like when people touch them, right? And this is exactly one of the possibilities how to work with such kind of grabbers for smart cells, for living cells, excuse me. Of course, these robots are without sensors because you cannot simply put standard sensors, rigid sensors on this soft actuators. And therefore, the skins which we discussed before, these magnetic field sensors, they come very naturally as control mechanisms for this type of robotic devices. Magnetism is history dependent. It's written in books. It's thermal effect, so thermally activated effect. So just imagine you have such kind of a composite which you overheat, or you can simply expose to strong enough magnetic field. You will change the magnetic state. This is obvious and trivial. For a robot, it's a disaster, right? Because it simply loses a state and it loses pre-programmed possibility to operate. And therefore, if you will put a magnetic field sensor on this thing, which has to be very soft, not to disturb these actuators, which are very weak and soft, you will be able to assess the state, and then you will know, will it operate as you programmed it or not, right? So this is exactly the trick behind it. And then you can use it for different use cases, because now you can use it as a origami, kirigami type of actuator, where magnetic field sensors, or the skins, can really control the folding degree. Is it properly folded? Did the folding process accomplished? Can you refold it again and fold from, I don't know, envelope to the plane, right? It's like a standard origami type of examples. That's why it can all be used. So this couple of examples which I presented to you now, just to show that curved magnetics in films, or curved spintronics in this case, it's something which is very interesting, very alive field of research. Now I want to answer the question, why do I present it here? Well, the reason is, and it became very clear recently. So the field is relatively new, right? So if you see this history presented by Dennis, it's about 10 years old active research on this field. And very recently, it became clear that the fundamental and application-oriented research here is very well connected. And the reason for this connection is very simple. Just have a look at this. You can ask yourself a question: if magnetic field sensors, they will have fundamental limitation on the limit of detection. So very simple question, right? Is there? In planar devices, you have very good excuses to tell, well, I can make it a little bit better film, I will reduce polycrystallinity, roughness of the edges. In principle, there is no limit of detection, yeah? Or you reduce temperature. In curvilinear magnetism, there is a limit, and at least it looks like now. So, and the reason behind it is shown here. So this is exactly what we discussed before. It's a skin, you put a sensor on the skin, and then there are wrinkles. Just imagine how your skin is working. So there are wrinkles, and these wrinkles can bring your magnetic thin film to a very high curvature value, right? One example is shown here. For example, this is a thin film, the very grayish stripe here in panel D. It's a 100 nanometer thick thin film. It can be bent upon such wrinkling to radii of a couple of micrometers, or if you will have a look on the small wiggles here, they're even in the range of sub-micrometer, right? So you can achieve very high curvature radii. And now it's happening very interesting thing. So I'm coming back to this very fundamental work of Alexei Volkov. They investigated parabolas. Why parabola? It's super simple object from geometry and from magnetic states which are there. So you can have either magnetization following the shape of parabola, or it can be saturated just to have a domain wall in a curvilinear reference frame there. Yeah? And now you do a very simple experiment. You just measure hysteresis, right? And then in the hysteresis, you will see that there is a switching field at about 20 millitesla, which does not exist in the straight stripes. So this, I will not discuss too much on the physics of this, but there is a rigorous way how you can experimentally and theoretically prove that this additional pinning field at low fields in hysteresis is due to the pinning of magnetic domain wall at the apex of the parabola, and the physics behind it is a curvature-induced Zaleshinsky-Fourier interaction. Yeah, so now we are coming back to this curvature effects, which were discussed before. And this is a beautiful effect, right? So if you will think from the fundamental point of view, it's a beautiful effect because, well, first of all, it's a first confirmation of all the theories which were presented before. It's a strong effect because if you will have a look on the strength of this effective Zaleshinsky-Fourier interaction, it's about the same as you can get in the asymmetric cobalt sandwiches, which people use for skyrmions and skyrmion bubbles experiments. But it's a terrible news for those people who are trying to make highly sensitive sensors, because it means that any kind of bend or twist, it's additional source of pinning of domain walls. It's additional mechanism of pinning and to increase the cursive field. And the cursive field, it's a limiting factor for any kind of sensitivity, right? So 20 millitesla cursive field means you can hardly sense with these devices anything which is below 20 millitesla. So this is a bad news for application-oriented community. And now there are a lot of activities and there are a lot of approaches how to, first of all, validate if this, what I told you, is correct by playing, of course, with the quality of films, trying to make this very high curvature racetracks in order to check whether there is a limit on sensing of magnetic field in these curvilinear structures. This research is now going hand in hand together. Therefore, there is, I think, only one field, which is curvilinear magnetism, which includes fundamentals and applications. And the reason for this is explained below here. It's primarily two sides of the same coin, because the sensitivity of the sensor devices is affected by local curvatures. And therefore, this understanding of fundamentals is very important to push forward the application scenarios. And at the same time, application examples here, they motivate further research in fundamentals, right? Thank you very much for your attention. I'm very happy to be here. I'm very happy to answer questions. Thank you.
Thank you very much for your very enlightening presentation with really a lot of examples of the use of this magnetism. Both, I think some of them can be a little bit frightening also, because you can use them in good sense, but you can probably also use them in a bad sense. But I like very much that your last connection between application and basic science. This is really important to emphasize that, and this is very important in our system of supporting science, that we all the time emphasize that basic science is necessary for application. We have time for some questions, if there's some questions immediately coming up here.
May I ask a question, Jens?
Yes, sure.
This is Larissa again speaking. Thank you very much, Denise, for enlightening talk. Could you please tell me if these non-invasive sensors can be used not in medical applications, but to carry the medical research on the magnetic field created by the joints, bending, unbending, brain activity, heart activity, blood pressure?
Yeah, this you're absolutely right. So this is exactly where one of very exciting application directions of those devices, because it's a lot of now activities on digital health. Means you want to put a lot of sensors on the body. It's not necessarily related to newborn or elderly people. It's in general trend to collect information on performance of athletes during fitness. It's very natural now. Of course, you want to make these systems wearable, and a lot of activities. It's a standard electrocardiography or something like this. It's already available. This is simple, but of course there are a lot of added value information, let's say in this way, coming from magnetism because of vector properties of magnetism for electroencephalography or even myography. What you can do, so myography is a muscle activity, encephalography is a brain activity, of course. Yeah? And the trick here is that detecting for encephalography femtotesla fields, or let's say higher femtotesla fields, it's possible with magnetoresistive sensors. Not easy, but possible. Myography would require sub-nanotesla, better like higher picotesla range fields. This is also possible, like planar Hall effect. That was our kind of attempt to detect these fields in flexible devices. Appears to be very difficult. So at the moment, we cannot beat nanotesla with flexible devices. And one of the reasons why we cannot beat it probably is related to this, what I called fundamental limit. This may be a little bit overemphasized, but maybe it's exactly this like result of what is happening due to curvature when you start bending device. So this is something which we are trying to investigate now. But you are absolutely right. Wearable monitors of magnetomyography, that would be something which is a big milestone for us, but also for other people in Asia, in Japan. They invest a lot of money, Korea, they invest a lot of money in exactly development of flexible wearable magnetic field sensors for health monitoring. Yeah, so this is very big research now.
Thank you very much.
Thank you.
We have another question from Helen, please.
Yeah, thanks, Dennis, for this nice talk. I have a question, maybe naive. So we are macroscopic people, yeah? So if we are talking about the devices which we would put on our hands, on our body, the scale is centimeters and millimeters. And on the other hand, we are talking about these nanoscale curvatures. So do we need to go deep into the nanoscales if we would like to think about the devices which are aimed at the human body?
Yes, you need to. That's exactly was a big question. Do you need or not? And this is a photo. It's rephrasing what Vladimir told. Mathematics doesn't lie. It's a photo, right? It's as simple as that. So this is a standard real curvatures which magnetic thin films experience if you just bend them. Skin can bend if you just put it here about 100%, right? So like stretch about 100%. If you will think about what is the wrinkling of the thin film, which will happen upon this stretching, that will be about this, what is shown here. So it's not so far-fetched from being real, yeah? What is important here, it's not the big bending radii, about 3 micron, which is already actually fairly small, but these small wiggles which are around. Yeah, and these small wiggles, it's something which we still, it's a paper from 2015, we still don't know why it doesn't break. So just think about it, you have 100 nanometers in film, which is bent with a curvature radii of about, I don't know, well, obviously sub-micrometer, and it doesn't break, yeah? So which friction effects are there on a nanoscale, right? Macroscopically, we probably don't see it, but what is a nanoscale friction effect? How does it pin the main walls there on these bands? This is something which contributes to the sensitivity of the sensors. Yes, it's nanoscale, but curvatures here are also not so far off, yeah? And therefore, surprising, yes, but for also this large area applications, you need to understand nanoscale magnetism.
But then the related question is also how, so with when you go to nanometer scales, then it's not the same magnetism as we have at the micrometers. So in order to have a magnetic order, you need to have enough magnetic atoms. So how relevant are these continuous models in application to the real nanoscale devices?
They're very relevant because
with a nanometer particle, you cannot talk about the same magnetism, and especially if you are going to more complicated structures than, for example, a ferromagnetic ordering.
Well, that's true. This will be discussed by Alexander for antiferromagnets. You are absolutely right. Well, we are not working here with nanoparticles. It's a still high quality thin film. Yes, it's maybe not a single crystalline thin films, but it's it's a fairly well exchange coupled thin film. So in this respect, continuum models I think are very, very valuable because they give you physical intuition, which effects are happening there and which effects you can start with to analyze the result of transport. So you measure some hysteresis curve. You have to understand how to describe it. And for this, you need a platform to start discussion. And then you can refine it. So you are absolutely right. This theory, which Vladimir, for example, emphasized on, yes, it does not include nanomechanics in a way. Striction is not there, which is very important, right? Because yes, we call something permalloy, but this is not permalloy in a sense of permalloy, right? It's a still magnetostrictive material what we are using. We are using cobalt. Cobalt is magnetostrictive material, this is not yet there, but it's a platform to build upon, right? And now there are a lot of activities stimulated by papers by Yuri, by Denis, by Vladimir to put simple strain, piezo effects, for example. It's at least restructuring the anisotropy constant. You can put flexo effects also. I think community is stimulated by your works there, and this is very important for this type of really application research. What are the flexo effects? Because you have inhomogeneous strain, heterogeneous strain, right? And all these questions, very fundamental questions, are not answered. So if you ask me the question, I do not know. We started to do this for magnetoelectric antiferromagnets, this chromium oxide with flexo effects. Would be very happy to discuss with you what is your opinion there. But bulk, awfully thick things, it's still very difficult. And we are not even curving them, So a lot of fundamental insights are still needed, but continuum models which are available now are very, very valuable to simply explain the effects which otherwise people have to, how should I need to rephrase Vladimir. So this framework of curvilinear magnetism for experimentalists, why is it important? Because it gives me the simple toolbox to start interpreting the results of experiment. If there is some chiral symmetry breaking, if there is additional anisotropy appearing, I don't need to understand the symbols, these omegas and everything in equations, but I need the solid conclusion. If I have an inhomogeneous texture, I could expect pinning on curvature. Okay, good. This already has measurable consequence, right? And this is a prediction of continuous model, which is very important here. Yeah. Very long, sorry, but hopefully at least partly answer.
Thanks a lot.
Thank you very much. I think we will close this session now and thank all the speakers again for very enlightening